secondary explosion could have had a yield of 3 to 5 megatons of TNT.
That is complete and utter rubbish. It's time for some more megaprojects. Specifically, the RBMK, the shoddy nuclear reactor that nearly killed millions. Really? Millions. Okay. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering to operations to emergency response. I don't think to know everything there is nuclear, but I can certainly share some knowledge. Let's see.
3 and 48 seconds, exactly, on the 26th of April 1986, reactor number 4 at the Chernobyl nuclear power plant in the Ukrainian SSR of the Soviet Union.
Oh, this is all from that HBO Chernobyl miniseries. If you haven't seen my reaction to that, I encourage you to check it out.
Exploded. And then, 2 to 3 seconds later, it exploded again. The single greatest nuclear disaster in human history had begun. At the center of it was a single, now battered and mangled, RBMK reactor, a device that had previously been lauded and celebrated as a monument to both socialist construction generally and the advanced glories of Soviet industry specifically, thanks to its ability to provide cheap and clean energy to countless people.
So, cheap and clean energy to a lot of people, that's the goal of nuclear power in general. Any nuclear power plant, that's your goal. Though, that wasn't the case here. The RBMK was originally designed to produce weapons-grade plutonium, meaning it used a higher proportion of uranium-238, which converts to plutonium-239 after neutron capture and a couple of beta decays. That happens all the time in nuclear power plants, but this additional focus on having that plutonium-239 does complicate reactor operation when it makes up a significant percentage of it. Oh, and by the way, in current nuclear power plants, the goal isn't to produce plutonium-239 for weapons. The plutonium-239 is simply fissioned within the reactor as part of a typical uranium fuel cycle.
However, it was but an obelisk to its blind naivety, one that was billowing radioactive material right up into the atmosphere and foreboded abject disaster if the situation wasn't brought under control and contained both literally and figuratively with all possible haste. And it is the RBMK reactor itself that we're going to be taking a look at today. Now, the disaster more broadly has been discussed many times. We've discussed it before as well, so there's no sense in retreading that stagnant water. But the reactor itself and its bungled design that led—
I don't know, he said this design nearly killed millions. I'd like to hear more about that, because the Chernobyl disaster did not kill millions. Officially, the number is 50. There are conservative estimates that take into account cancer cases over time, including those of people that haven't been born yet, that have given it a figure of 4,000, but no nuclear or medical organization has ever given numbers in the millions. But maybe he's talking about something else.
Disaster. That's something that is pretty underappreciated. So let's get into it.
Okay, let's see how he does.
All right, before we get into the meat of today's video, it is worth us taking the time to get our heads around how nuclear reactors actually work. Partly, this is because it'll be a useful grounding for the rest of the video, but also just due to the fact that it's interesting. And if you found yourself on this channel, we're going to assume
one of the main reasons why I became a nuclear engineer.
That you like machines, particularly big and powerful machines. So let's begin the explanation with the basics. That being that nuclear reactors, they produce energy via the process of splitting atomic nuclei, a naturally occurring phenomenon dubbed nuclear fission. In man-made environments, this naturally occurring process can be concentrated and made controllable. It then produces an immense amount of heat, which is used to boil water, creating steam, which is then used to spin turbines attached to—
So this diagram here is you have your basic pressurized water reactor. The RBMK is a type of boiling water reactor. Kind of a weird one. I'm sure I'll show a diagram later, but this isn't what an RBMK looked like. This one is actually more basic, and you can replace the nuclear reactor on the left with a coal or natural gas-fired boiler, and the rest of this diagram basically looks the same for other forms of generating electricity through a steam cycle.
Great generators, and there you have it. Boom, electricity. Who needs a degree in nuclear science? But it really is—
I feel like I should say something to that, but technically my degree is in nuclear engineering, but it includes a lot of nuclear science as a prerequisite.
Remarkably simple process at its core. A real challenge in all of it comes from allowing nuclear fission and the subsequent production of electricity to happen efficiently, and above all else, safely. Now, To go into a bit more depth so that we can show you what we mean about the challenges here.
Yeah, I'm not sure what he means by the word challenge. I mean, I guess if you're looking at all the supporting technologies required to build and operate a nuclear power plant, then sure, just building large pressure vessels, steam generators, requires a lot of support technology. Nuclear power, unfortunately, isn't one of those things you could take back into a time machine to a primitive time period, and even expecting the smartest people of the world to know how to do, simply because you're lacking in theory and supporting technology. Also, time machines wouldn't work like that, but I digress.
Nuclear reactors operate by initiating and maintaining a so-called sustained chain reaction, i.e. a continuous series of nuclear fission events where each reaction produces enough neutrons to maintain the process at a steady rate, giving you a constant flow of heat, therefore.
So when he means steady rate, that is what critical actually means. Criticality is when the total population of neutrons is the same, so reactor power is stable, unchanging. And that's where nuclear power typically sits. You typically go up to 100% power and you stay there, as nuclear power is base load. You very rarely see it in a load-follow configuration. It's much less efficient that way.
A flow of steam and boom, electricity, happy days. As for what that fission event that actually splits the fissile atoms is, it's a simple collision, specifically a collision between neutrons and the nuclei of fissile atoms such as uranium-235. 235?
So collision isn't wrong, but one thing I just do want to emphasize is, I know these are simplified diagrams, this isn't what the nuclei actually look like. You're not bowling and getting them to split kind of like that. The uranium, it's a neutron and then splits. It's not like some of these diagrams illustrate, though it is a simplified way of thinking about things.
It refers to the mass number of the uranium, which is the total number of protons and neutrons in the nucleus. 92 protons, 143 neutrons. There are also other sorts of uranium, such as 238, which has 92 protons, 146 neutrons, making up its mass number, but this is not fissile. That's for why, to simplify it just a little bit here.
So uranium-238 is not fissile, but it is fissionable, meaning that it is possible for it to fission with a fast neutron, though it's not sustainable because the odds of that are pretty low. And not to mention, most nuclear reactors don't operate in a fast neutron spectrum, and even if they did, you're better off using other fuels than uranium-238. But you can technically fission uranium-238. You can also indirectly cause conditions that lead to fission by having it absorb a neutron and it becoming plutonium-230. Absorbing a neutron, couple beta decays later, it becomes plutonium-239, and that fissions. Or you can keep the plutonium-239 and use it to make weapons.
Uranium is quite happy and content with 146 neutrons, and very unhappy with 143 of them, and so with 143 it becomes unstable and is more susceptible to having its bonds messed about with.
Not bad explanation, but uranium-238, you can call it stable, but it technically is still radioactive. It has a half-life of 5 billion years, and it's an alpha emitter, so it's pretty slow. And for all intents and purposes, you can consider it stable, but it's technically not stable. Anything that's radioactive isn't stable.
It wants to get to its happy place. Fission event, as you might have already deduced from this, also releases a lot of energy, with the energy released from but a single gram of uranium-235 going through fission being equivalent to the energy that's released by burning 3 tons of coal. Primarily, this energy comes...
Yeah, that's a lot. And with that in, fuel proportions, a uranium fuel pellet, uranium oxide pellet the size of a pistachio is more than a ton of coal. Very energy dense.
Of kinetic energy, which keeps the atoms moving and enables that sustained chain reaction, and heat, which is then harnessed to boil that water and generate that electricity. A question though, because if you have a whole lot of fissile material inside of a reactor bouncing about the gap and having a grand old time splitting away, what stops the total reaction rate from just exponentially growing to both literally and figuratively explode? Well,
it's about having equilibrium. There are things that increases the chance of fissions, and there are things that decrease the chance of fissions.
Left to do its thing, absolutely nothing at all is the answer to that. And so, if left to its own...
No, that's not at all true for a nuclear power plant. Not the left to its own devices sort of thing. If it would shut itself down when you exceed a rate set point if power happens to be going up in an uncontrolled manner, but I digress. No, nuclear weapons are designed that way, but they are designed to be something that is called prompt critical. So after each fission event, some neutrons are released right away, and then some neutrons are released considerably later. Those are called delayed neutrons. And to give you a sense of the speed, prompt neutrons on the order of 10 to the minus 14 seconds. So you might as well just say they're instant. Delayed neutrons, seconds to minutes. Now, prompt criticality is essential when designing a weapon because you want it to fission really quickly, generate a lot of heat, and in a modern thermonuclear weapon, you're going to want that heat to generate conditions strong enough to induce hot enough and under enough pressure to cause nuclear fusion with the fusion stage of your weapon. That's what it's supposed to do. Now, a nuclear power plant, you want it to be delayed critical or just critical. When people say critical in the event of a nuclear power plant, they mean delayed critical. That is to say, the prompt neutrons by themselves are not enough to sustain a fission reaction. You're dependent on the delayed neutrons, which, considering they take time, a lot of natural and artificial feedback mechanisms to control the reaction slow it down. But keep in mind, even some of them are natural, like temperature. If fuel heats up too much, the reaction's going to slow itself down. Now, yes, Chernobyl went prompt critical, but I'm assuming we'll get to that in a little bit.
Devices, that's exactly what a nuclear reactor will do. It'll just keep going and going and going, and then bang! Once the reactor can...
Badly designed reactors where people fail to adhere to their safety procedures, defeat all of their safety systems, and put themselves in conditions to add reactivity, that is to say, raise reactor power multiple ways at once while essentially cutting their brakes. Nowadays, you couldn't even get a loading pattern where this would be physically possible, a fuel loading pattern where the fuel has enough energy to do something like this.
Longer contain the pressure, it explodes. As a result, you need systems and mechanisms that allow you to calm down the reaction rate to keep it at a nice...
So note that when he's talking about reaction rate, he's showing a picture of cooling towers. Yeah, what you see here has nothing to do with the nuclear power plant. This is in the secondary non-nuclear part of the facility. In fact, I can't see behind all of the steam, and that's what that is. That's just water vapor, because all those things do is they cool the condenser. I can't even tell if this is a nuclear plant that he's showing. It probably is, but you can't tell just by looking at this picture. I don't see I can't see if that's a reactor building, a reactor containment dome behind that steam.
Balance between producing plenty of heat, but not so much that it gets out of hand and then becomes really, really dangerous. This is done through the use of coolants and moderators. A coolant, that's exactly what it sounds like, something that is pumped into the reactor to absorb the heat of the fissile events. Usually it's water or gas that's used for this purpose, which also in turn then goes on to power the turbines when heated up.
It was water in the case of Chernobyl, even. It's also water in the case of most nuclear power plants.
Moderators, on the other hand, they directly disrupt the rate of fissile events in the reactor.
That is completely wrong. Moderators slow down neutrons so they are slow enough to cause fission reaction. They exist so you can have a fission reaction. So they actually do the opposite of what he says.
Calm things down that way. They can also be the same substance that's used as coolant, with water, for one example, also being used in this way, because whereas it will absorb heat, it will also slow down the neutrons produced during fission.
No, he's got that completely backwards. No, they increase the amount of fissions by slowing down the neutrons so they produce more fission. And in a reactor that uses water as the coolant and the moderator, such as a pressurized water reactor, the moderator temperature coefficient was negative. And when I say when I say coefficient, I mean thing that affects reactor power, thing that affects reactivity or reactor power. A positive coefficient, which means if said parameter goes up, reactor power goes up. If said coefficient is negative, then more of that parameter causes reactor power to go down. So when I say a moderator temperature coefficient is negative, that means if temperature goes up, reactor power goes down, which is a great built-in feedback mechanism. Because if you cause too many fissions, but let's say you have a reactivity excursion, fissions go up, it heats up the water, but the moderator temperature coefficient slows down the fission reaction because it got heated up. It's a great natural feedback mechanism.
There's various mechanisms that can be used to slow down the rate of reaction, chief among which are control rods. Composed of
he's right
materials
about
like
that one.
boron or cadmium, these rods absorb excess neutrons which would otherwise be off on their merry way to produce more fissile events and thus allow operators to regulate the reaction.
Basically how they work is they have a much greater chance of absorbing neutrons than uranium-235 does of causing fission. So you insert them in, depending on how far you insert them, you're going to significantly slow down the reaction.
And this really does work incredibly well, as during the 3 Mile Island incident, for example, the rapid insertion of all the control rods completely halted the nuclear chain reaction, preventing a catastrophic meltdown despite the fact that the reactor had lost the bulk of its coolant and
No, it did not prevent a meltdown. It prevented a significant accident, and this accident is overblown, but a meltdown did occur. Fuel did melt. The core was severely damaged, but it was all contained. So no, the control rods did safely shut down the reactor, but they did not prevent a meltdown.
And do remember control rods, as they will become very, very important in the Chernobyl story later on today. It's also worth noting that different reactor types have evolved differently to optimize the balance between safety, efficiency, and economic viability as their creators see it. This has led to the creation of 2 dominant reactor types: pressurized water reactors, or PWRs, and boiling water reactors, or BWRs.
Thus far, though, in general, man, he's not off to a very good start, is he?
Former uses high-pressure water to transfer heat to a secondary loop for steam generation, while the latter generates steam directly within the reactor vessel to drive turbines. Alright, so
Okay, I mean, that was a good oversimplification, and RBMK is a type of boiling water reactor, though one of the chief differences is water is just the coolant in an RBMK, not the moderator. That one uses graphite, but I'm sure we'll get into that.
Much about the technical nitty-gritty of those 2 types, but what we really want you to take away is the fact that they are the dominant types, and the RBMK reactor is neither of them. It instead...
Technically, it is a type of boiling water reactor. It's a very weird one, and he means it's not your standard boiling water reactor that you see all over the US. I'm going to argue it's a boiling water reactor because water does boil within the primary loop. Yeah, on this drawing right here, the steam separators are directly connected to each channel of the core. If they were separated by something, then I would argue it was not a boiling water reactor.
Its own unique thing that uses graphite as a moderator and water as a coolant, and it also makes use of individual pressure tubes for each fuel assembly. That last detail in particular is interesting. For starters, it's why RBMK reactors look so weird compared to other types, with the hundreds of squares arranged in a big circle, each one of them a fuel assembly. But
one of the reasons why that is the case, why it's so big, is because it's not as energy dense. Because here their goal isn't just to make power, their goal is to make a bunch of plutonium-239. Well, if you're going to use some of that for not making electricity purposes, if you still want a megawatt, if you still want a gigawatt going on your grid, you're going to need a lot more fuel going at once. This RBMK had relatively low enrichment.
So interesting as a choice that reflects the issue with the RBMK: cost cutting. You see, while such a design does have legitimate advantages, such as being able to refuel while the reactor is in operation by just popping those fuel assemblies out and quickly sticking in a new one, in reality the major advantage was cost saving. Such a design allowed the Soviet Union to avoid having to manufacture a single, robust, and enormous pressure vessel for each of its reactors, something that was both expensive and really, really difficult given the state of Soviet industry.
Yeah, and to add to that, they didn't even put a reactor containment building to essentially protect if all of the energy became released in some catastrophic fashion, which is what happened in Chernobyl.
I think the lack of pressure vessel is bad, given, explosions and all that. Well, that's nothing compared to the fact that the RBMK worked using something called a positive void coefficient. More generally,
I was going to say that I actually thought he was going to mention the lack of containment building.
Coefficient, when it comes to nuclear reactors, refers to how the reactor's reactivity changes when steam bubbles void, replacing liquid coolant in the reactor core. A positive one of those, as in an RBMK, means that as steam bubbles form in the coolant, the reactor's reactivity increases instead of decreasing. Literally positive, it goes up. This occurs because steam absorbs fewer neutrons than liquid water, allowing more neutrons to sustain the fission chain reaction, which can lead to a dangerous feedback loop of rising power.
So let's talk about the effects of boiling and why. So, as he's mentioned, the RBMK uses graphite as a moderator, and water acts only as a coolant and absorbs the neutrons, reducing reactivity. Now, I say water is acting only as a coolant. Water as since it's a liquid, not nearly as densely packed or as effective as graphite is as a moderator. So, yeah, it technically moderates a little bit, but not very much compared to the graphite. You gotta view reactivity as kind of like a supply and demand. So, when boiling occurs, voids form, fewer neutrons are absorbed by the water. So more neutrons remain in the core, which increases reactivity, which is why you increase the number of voids, reactor power goes up. Compare that to a boiling water reactor, and I'm referring to a regular boiling water reactor that is both moderated and cooled by water. Water slows down the neutrons and absorbs some of the neutrons. So when water turns to steam, there is less liquid water to slow the neutrons down. There's no graphite to always moderate it. So the net result is slowing down your neutrons. So fewer slow neutrons lowers reactivity and lowers reactor power. So boiling water reduces neutron moderation and ultimately reduces reactor power. I wonder if he got confused about this when he said moderators slow down the fission reaction, because that's just not true.
In contrast, a negative void coefficient, as you find in both PWR and BWR reactors, works in the opposite way.
We do talk about the void coefficient in the context of a pressurized water reactor. It looks a little different. You could argue in the case of a pressurized water reactor, they have a positive pressure coefficient because when you raise reactor pressure, reactor power goes up. A little bit, not very much, considering it's a much lesser effect than what you would see in a boiling water reactor. But you raise pressure in a pressurized water reactor, you collapse the voids and you have the same mechanism as you collapse the voids, void coefficient is negative, so raising pressure, less voids, reactor power goes up, but not very much. This is a much bigger deal in boiling water reactor. The moderator temperature coefficient is dominant in a pressurized water reactor.
Steam bubbles form, the reactor's reactivity decreases. This happens because the reduced density of the coolant absorbs fewer neutrons, but instead of increasing reactivity, the slowed reaction rate stabilizes the system. This negative feedback loop acts as a natural safety mechanism, preventing the reactor from overheating and helping to maintain steady operating conditions even during power fluctuations. A positive void coefficient, naturally, is not ideal. Think of it almost like air brakes on a railway locomotive.
Now, one thing I don't want you to take away is a positive void coefficient is dangerous, or makes a reactor dangerous. It made Chernobyl bad. It made Chernobyl dangerous, but by itself, it doesn't make a reactor dangerous. I mean, take a sodium-cooled reactor that runs on fast neutrons. It's got a positive void coefficient, though it has other feedback mechanisms that counteract it. First off, it doesn't have a moderator at all. I mean, it uses fast neutrons. You don't need one. Another thing is liquid metal doesn't create voids easily, so it's less relevant. And in that reactor type, it's dominated by the fuel temperature coefficient, the Doppler broadening coefficient, where if you raise the temperature of the individual fuel, it stabilizes reactivity, offsetting the void coefficient. So the void coefficient wasn't the only reason why Chernobyl was bad. There were quite a few.
there's constant air pressure being applied, which makes the brakes ease up. If you remove the air pressure, they clamp down and stop anything going awry. It's far safer than having brakes which are unapplied by default and so risk being locked in the open position during operation. A nuclear reactor with a negative void coefficient that naturally wants to reduce its reactivity as steam is generated and requires a bit of energy to keep that reactivity up is far safer than one which naturally wants to rise and requires effort to push it down instead. Far better to have a cold reactor in the event of a whoopsie-daisy than a blown up one.
So he mentions cold reactor. I'm going to challenge that one thing, and I mentioned moderator temperature coefficient is negative. So if you have an excessive cooldown in a reactor, that's going to raise reactor power. So you do not want a reactor to be cold. Worst case scenario, you can restart or shut down reactor. That would take a significant excessive cooldown, such as a main steamline break or really multiple main steamline breaks, and could require instances like emergency boration, basically inject boric acid through the emergency core cooling system in order to shut the reactor back down. Safety injection, and a reactor would already shut itself. During a main steamline break, though, all the control rods are already fully in, and safety injection will already be initiated, but there will be a few seconds where the reactor could restart depending on design. So I don't like the term cold reactor. Plus, you got to worry about pressurized thermal shock. Generally, when any pressure vessel gets rapidly cooled down and rapidly pressurized, you got to worry about things like brittle fraction. So, can't say I'm a fan of a cold reactor either, especially when it happens quick. You need to safely and controllably cool. You need to cool down your reactor in a very safe and controlled manner, is all I'm saying.
Positive void coefficient is something you can work with, and it's no major issue. But if, say, you find yourself in a situation that is getting a bit tense and you're immediately...
Its big weakness is in low power. Because at low power, any coefficient has a larger effect, because back to supply and demand, a little bit of something causes a lot more effect because you're at low power.
Priority is killing reactivity for the sake of safety. Do you think the whole initial spike in reactivity when you add more coolant thing might just come back a bit to bite you on the arse?
Okay, and he did mention the whole initial when adding coolant or lowering temperature. Okay, so he at least aware of that.
Certainly did at Chernobyl, as we're slowly getting to. And speaking of going forward, since we've drifted out of general reactor principles and into explaining the RBMK specifically, let's knock this chapter on the head before we go any further.
Okay, let's see what he says.
Now, where were we? Yes, that was it. The RBMK being a total heap of junk. And let's continue the explanation by coming back to control rods. Because given that they are...
I have heard a few people in the nuclear industry refer to RBMK as a really badly made kettle. After all, a lot of nuclear power plants really are just kettles, boil water.
Trying to not just keep the reactivity manageable, but also be the last line of defense against disaster by being able to all just be slammed in on one another and kill the reaction dead. I mean, how big of a tit do you suppose you'd have to be to tip your control room rods with a material that increased reactivity? Well, the answer to that would be big tit, because that's exactly...
Can't say I've heard anyone refer to it as that, but... All right. One thing about the tips, just the tip is a bit of an understatement, as in the tips were fairly long. Like, it wasn't just a teeny tiny portion of the control rod. But yes, you're having something that accelerates a reaction at the tip of something that's designed to slow down a reaction. That would be a bit like when you slam on the brakes, you hit the accelerator for a split second.
They chose to do with the control rods being mostly boron carbide with just a little smidge of graphite on the ends. And look, contrary to what a certain 2019 television show would have you believe, the control rods were not graphite tipped to save on cost, and instead they were designed that way to enhance neutron economy, i.e. the efficient use of neutrons to sustain a controlled chain reaction by maximizing.
And this is yet another weakness specifically at low power, because you're vulnerable to these sorts of surges and transients when you insert control rods.
Events while minimizing losses through absorption or leakage, and graphite, despite being an excellent neutron moderator, slows down vast neutrons into thermal neutrons that are more likely to sustain the nuclear fission process. When the graphite tips were inserted into the reactor, they displaced neutron-absorbing water in the control rod channels, momentarily increasing reactivity by boosting the local neutron flux.
And notice this is an important thing to bring up. It increases it at the bottom of the core. Axial flux, which is how much power is produced at the top versus the bottom, is something that nuclear engineers and reactor operators monitor very closely. You do not want to have these sorts of spikes like this at the bottom of your core. I mean, naturally, it's always going to be a little bit just because of the shape. You insert control rods, it's going to lower neutron production at the top and shift it towards the bottom. But you don't want it like Exhibit C here.
This design choice was made to improve reactor efficiency and operational flexibility, especially at lower power levels. Essentially, you could...
I call BS on that. There's no way that improves any efficiency, and it makes operating at lower power levels just a pain. For lack of a better term, I couldn't imagine as a reactor operator trying to operate something like that, especially because with some of their technology a secret that is beyond the scope of some reactor operator training.
Reactor efficiency and operational flexibility, especially at lower power levels. Essentially, you could...
Especially considering that some of that is been withheld from said reactor operators.
The reactor with just the tip of the control rods to keep its reactivity up, and if you wanted to kill reactivity...
I mean, I know just the tip is the obvious joke, but... It's a big tip.
You could just push through that spike, at which point the boron carbide would start doing its thing and reduce reactivity far more than the graphite was increasing it. And if you're wondering what that little spike of reactivity from the tip of the rods would do to an RBMK reactor that was right on the brink of going bang, if you were to say slam all the control rods to initiate an emergency scram shutdown and kill the reactivity just like they did at 3 Mile Island, well, hold that thought, because...
Another thing is they should have shut down the reactor way earlier than they did when they had all of essentially that positive reactivity wound up. If they would have scrammed the reactor, or tripped the reactor, that's the term I'm used to, earlier into that event, you wouldn't have an accident.
Where this is going. Now look, there's a lot more we could talk about, as the RBMK reactor was just full of unnecessary cost-cutting measures, such as the lack of pressurized containment vessel and weird little design.
So when he says pressurized containment vessel, he's referring to the reactor vessel itself, but the fact they didn't even have a reactor building, a reactor containment building, because you want both. You want one around the reactor itself, and then one around the actual building you place the reactor in. They had neither.
Such as the graphite-tipped control rods, but as our main goal here is just give you a detailed enough understanding of both nuclear reactors generally and the RBMK specifically, so that you have a good idea of what happened back in 1986, we'll just leave it there. And that means that we can get on to the main event of today's story. Now, the sequence of events that led to the disaster began with preparations for a planned safety test designed to evaluate the reactor's ability to maintain cooling during a power loss. In short, using the energy present in an already spinning turbine to keep the reactor's coolant pumps going during the minute or so that it took for a set of emergency diesel generators to kick in and take over. This test...
That is also abysmal. They had bad diesels. Nowadays, forget your minute. 10 seconds is from loss of power to diesel output breaker closing, and it's supplying the critical bus you need to safely shut down the reactor.
Required the reactor to operate at a reduced power level. However, RBMK reactors, as explained earlier, were highly unstable under low power conditions due to their positive void coefficient. Despite this
their positive void coefficient, the control rod design flaw, its susceptibility to xenon-135 buildup, that's true in every reactor, but you don't want to do this sort of experiment at low power, because Chernobyl especially was even more vulnerable at low power. It's slow diesels, it's slow emergency core cooling system, and one other thing about it being a channel type reactor instead of one pressure vessel is you can have a leak in one individual channel that could go undetected for a while before things get really bad. And by things go really bad, I'm referring to fuel leaks, pressure surges, so even small steam explosions from, say, something going wrong with one fuel channel could damage the rest of them, and you can have a cascading effect. That's only an issue if something else already happens first, but yeah, it's there were a lot of issues with this reactor design.
Plant operators faced significant pressure to complete the test, leading to the circumvention of key safety protocols. Automatic shutdowns.
He mentions plant operators when referring to guys in the control room. Sure. There's a big distinction, at least in the US, between plant operators and reactor operators. Generally, plant operators are out in the field and reactor operators are in the control room. There's specific licenses that you're required to hold within the US. A reactor operator license, you have to get licensed through the Nuclear Regulatory Commission, and there's a separate one for their supervisors, senior reactor operator license. That's the one I had, and yeah, it's quite a rigorous process. Takes a couple of years, a lot of technical classes, a lot of simulator drills, a lot of individual drills, and a lot of things you have to do under pressure while being evaluated by a regulator following you around with a clipboard, watching everything you do.
Were disabled, and the emergency core cooling system was overridden, removing critical safety layers. At midnight, operators attempted...
Yeah, nowadays, physically impossible to do via interlock. In order to defeat your emergency core cooling systems, your reactor has to be off.
lower the reactor's power output, but a procedural misstep caused the power level to plummet to near zero.
It wasn't a misstep, man. They deliberately deviated from their procedure in the non-conservative direction. It was already a non-conservative procedure.
Nearly all control rods were manually withdrawn to restore power, an action that drastically reduced the reactor's safety margin. By 1:23 a.m., the reactor was in an extremely precarious state, with minimal coolant flow, a dangerously high positive void coefficient, and almost no control rods in place.
Technically, the coefficient didn't change, but they had a dangerous number of voids. So I guess you can say the integrated coefficient put them in a bad state.
The test commenced, triggering a chain of events that quickly spiraled out of control. As the turbine slowed, the coolant flow decreased, and steam began to form within the reactor channels. Due to the RBMK's positive void coefficients, the formation of steam caused a rapid increase in reactivity. This feedback loop escalated the reactor's power output, pushing it far beyond safe operating limits. The operators activated the AZ5 button to initiate an emergency scram shutdown, inserting all control rods simultaneously. However, as detailed earlier, the control rod's graphite tips temporarily increased reactivity upon insertion. This design flaw caused a sudden and catastrophic power surge. Within 3 seconds, the reactor's output skyrocketed.
Even in RBMK's design, if they didn't defeat everything, the reactor would have done that by itself long before they approached this dangerous position, due to that crazy overpower events, power being out of band, temperature being out of band. Basically, they should have done an emergency shutdown 10 different ways before they actually did, and unfortunately it was too late.
To an estimated 10 times its maximum capacity. The intense heat generated during the surge caused the fuel rods to rupture and the reactor's pressure tubes to burst. The resulting steam explosion destroyed the reactor core and blew the 1,000-ton upper shield into the air, straight up and out of the reactor building via the roof. The explosion...
Well, at least the reactor shut down at that point. Because it's in pieces, it can't sustain a fission reaction if there's no bits of reactor right next to each other.
Exposed the graphite moderator to the atmosphere, igniting fires that further spread radioactive material. A secondary hydrogen explosion caused by the zirconium water reaction compounded the devastation. The initial blast...
Yeah, so the zirconium in the fuel assemblies is what that is. And now zirconium interacting with water normally doesn't do very much. But when you get to temperatures above 2,000 degrees Fahrenheit, then yeah, that starts to rapidly accelerate. Then that reaction takes off and produces a lot of hydrogen gas.
And subsequent fires released a massive plume of radioactive isotopes, including iodine-131, cesium-137, and strontium-90 into the atmosphere.
So iodine-131 is probably the most hazardous immediately after the accident. In nuclear power plants, we often measure in terms of just dose equivalent iodine-131. Though, as far as the hazard that's still there now, it's going to be cesium-137. That has a half-life of about 30 years, and it's a metal. It can get into the ground, so that's the bits that are still radioactive today. And that steam plume looks scary, but ultimately a lot of the damage was a lot more localized than some people claim.
Emergency responders arrived quickly, but they were ill-equipped for the scale of the disaster. Many were unaware of the radiation levels they faced and worked without adequate protection.
Yeah.
Their efforts to
no
extinguish
radiological
the fires
safety
and
brief.
stabilize the site were heroic, but they came at a great cost. Dozens of first responders succumbed to acute radiation sickness within days, and many more suffered long-term health consequences. Estimates of the death toll from Chernobyl vary widely. The International Energy Agency, for example, reports that there were approximately 30 immediate deaths among plant workers and first responders, immediate in this instance being defined as death within a week or so for radiation exposure on the night of the explosion, with a further 30 or so being added for deaths caused by radiation exposure among those groups immediately after.
That's not far off, 30 or so immediate, with up to 50 from the longer-term cancer effects.
But that took longer to claim their victims. This is roughly in line with the Soviet Union's official stance, which, right up until its collapse, maintained that only 31 people were directly killed by the disaster, all of them being plant workers and first responders. Both figures, however, mask an unpleasant reality. That being that the true death toll is much higher. So high, in fact, that if we...
So when you look into other things, I think I know what he's referencing. He's going to reference the 4,000 number. But that takes into account the linear no threshold model, which is a very conservative way to measure. And it's assuming every individual little bit more radiation you got has increased your risk of cancer. That includes things like eating a banana and sleeping next to your partner and cuddling your spouse. The linear threshold model, which is much more widely used, has a number. It's 100 millisieverts, which is twice the annual dose limit for a radiological worker, or 100 times the US dose limit for a member of the public. And that is where you start accruing increased risk of cancer. But if you use the linear no-dose model, yeah, the number you come up with is about 4,000.
A lens of lives shortened because of the disaster to get a more accurate picture, that initial figure of 30 to 60 or so leaps, with the UN placing the figure at 4,000 and Greenpeace and the book Chernobyl, Consequences of the Catastrophe for People and the Environment, placing the figure at up to 200,000 and 900.
Oh, Greenpeace? Yeah, you know they're making stuff up. They're completely full of it.
And 85,000 respectively. Now, this huge variation in total predicted death toll is rooted in the simple fact that linking specific cancer cases directly to the disaster remains very challenging due to a plethora of difficult-to-gauge factors such as general background radiation exposure, genetic predisposition.
Cancer is a probabilistic. Trying to fingerprint cancer is challenging to do. And yeah, there's too many confounding variables.
Positions and variations in data collection methodologies across different regions, and all of that's before you even get to the matter of the latency period of radiation-induced cancers, as cases may emerge years or even decades after initial exposure. But while we know for
So that's potentially true, but a lot of it is more earlier onset, at least with the majority of cases.
That the real figure is far higher than it initially appears, whatever it may actually be, the truly mind-boggling thing about the death toll is that even despite the inflated true figure, things could have easily been way worse.
Why is he saying if it's true and inflated? That's contradictory. Also, don't use the term true figure. I do not like that assessment. It's like just say the initial figures, because that's what they are. They're initial. We all know they're low because it has the word initial by it. We know the 30 number is low. We know the 50 is an extrapolation. We know the 4,000 is a very conservative extrapolation. We know the Greenpeace figure is complete BS. Just, I don't like the whole true thing. Just everyone has their own qualifiers.
Had the disaster played out differently? Among the chilling possibilities was the risk of a second explosion, one that would have been inconceivably more devastating than the one we did get. You see, after the first explosion ruptured the reactor core, intense heat from the molten fuel rods began melting through the reactor's base, and beneath the reactor lay a large water reservoir, part of the emergent cooling system. Had the molten core material, or corium as it's known, reached the water, a massive steam explosion could have ensued, and according to physicist Valery Legasov, such a secondary explosion could have had a yield of 3 to 5 megatons of TNT.
That is complete and utter rubbish. It is physically impossible for any power reactor to produce an explosion in the megaton. That's big even for nuclear weapons. This Legasov claim had to have been a misunderstanding or some exaggeration. I heard it in the Chernobyl series. Hearing this again makes it one of the worst videos I've seen on this guy's channel, I'll tell you that much, as far as accuracy. So let's put that in perspective. The actual Chernobyl explosion, a couple hundred, maybe 300 tons of TNT. I mean, yeah, it was big. It was a reactor going prompt critical that shouldn't have because of all the individual increments of adding positive reactivity with no safety systems. It was bad. And yes, the steam explosion would have been bad, potentially worse. We're talking maybe a kiloton at most. And that's assuming no energy loss and the carcass of the reactor landing beautifully and perfectly within the steam, within the water underneath, so that it creates a nice, neat steam explosion. The reality would be, it would be kind of a sputter of a bunch of smaller explosions. But yeah, there's just not enough energy in that system to go anywhere close to megaton range. That statement is complete BS.
If you compare that to an American W-87 warhead, which is used in the Minuteman ICBM, well, that's got a maximum yield of only 475 kilotons.
No, that should tell you right there how wrong this is. I don't know if it's this guy or his support staff or maybe some AI-driven tool that fed him that pulled information from HBO's Chernobyl like it was a reliable source. But come on, this is some, of all the Chernobyl myths to perpetuate, this is bad.
Map as our reference here, as their math is actually very, very well done. Such a blast at its
unlike yours.
Predicted yield of 5 megatons at ground level would have made a fireball big enough to completely burn the towns of Pripyat and Chernobyl off the map, killing.
Sure, 5 megatons, that's a sizable nuclear attack. Yeah, you hit that with 5 megatons of nuclear weapons. Sure, I'm not questioning that. What I am questioning is that this is 5 megatons, because it's not. It's not 1,000th of that.
Every single one of the 63,000 people who lived in those two cities instantly. And that was the.
Let's say it is 5. Let's say it is 5. Where is he getting could have killed millions from?
Radiation, as not only would nearly all the radioactive materials of Reactor 4 be thrown up into the atmosphere, but so would that of Reactors 1, 2, and 3, as they would be absolutely obliterated by the blast.
Okay, and let's say, all right, your magical fake nuke thing, and you had 4 of them. Okay, so 20 megatons of BS logic-driven explosion. Don't underestimate the power of that. That's still not going to get you to millions of casualties.
Exact numerical predictions for the total death toll are hard to come by, not least due to the fact that the number of variables
it's ridiculous.
Make it almost a matter of quantum science to begin trying to figure out. But to give you an idea, Valery Legasov predicted that such an event would render the Western Soviet Union.
I'm not convinced he did. Maybe numbers were taken outside of context so he could pressure party officials to do something about it or something. But I'm thinking there's some exaggerations, possibly translation error as to what is causing this.
Eastern Europe and even slithers of Central Europe totally uninhabitable for centuries.
Also for centuries, where are you even getting it? Chernobyl, the area around Pripyat isn't uninhabitable now. And I know radioactive isotopes can stay around. Cesium isotope has a half-life of 30 years, so the usual rule of thumb, by the way, is 8 to 10 half-lives, depending on how conservative your health physics team is. You can call something gone. But yeah, there's just not enough radioactive material to go around. I don't know, maybe with some magical stuff, even if you salted it with cobalt-60 decays faster than that. So no, I can't think of a scenario to even make this ridiculous claim realistic. Probably because it's not.
The Chernobyl exclusion zone was hard enough, so to do the same for half a continent would be flatly impossible.
It's habitable. It is just what is known as a radiological controlled area, which means you have to have dosimetry, you have to have permission, you have to be monitored in order to enter it. safely and under supervision. It does not mean you step 1 foot, you're going to get radiation sickness. It's not even remotely true.
Of course, those living under the vast cloud of radiation as it settled would also be condemned to death sooner or later, and that's
not even remotely true either.
Untold millions of people. But while that alternative scenario was by far the most terrifying, there were others that...
Yeah, it's terrifying because it's wrong. I know I'm dunking on this guy a lot, but this is bad. I know this scene was in the HBO series, but this is worse because, for one, this intends to be educational. The HBO series was a drama, and you could even argue that the character in the show used it just to be dramatic, just to get the Soviet officials to do what they wanted to do. For all we know, he completely made that up in the context of the narrative of a TV show. But this is horrible.
Presented the possibility of the disaster being far worse. For example, another scenario involved the possibility of widespread ignition of the reactor's graphite moderator. The initial explosion and subsequent fires exposed portions of the graphite core to the open air.
Hell. Okay, so what are we saying? It's gonna open up a portal to hell? Well, if we're using fiction, let's just go ahead and call in the Doomslayer. He'll take care of them. What is this?
It could have easily caught fire and spread uncontrollably. A fully engulfed graphite fire would have dispersed radioactive particles over a far greater area than the actual disaster.
So here's the thing about dispersing radioactive particles over a far greater area. It gets diluted. So you can make some bizarre, scary cloud drawing if you would like, but you could actually argue that could produce less casualties because it's less concentrated, less likely to get somebody sick.
Due to the unique thermal and chemical properties of graphite. Graphite, which serves as a neutral moderator in RBMK reactors, is highly combustible when exposed to oxygen at high temperatures, as it can sustain a fire even under...
I don't know, this guy apparently thinks moderators slow down fission reactions, so it's probably fine.
...oxygen conditions. This risk was exacerbated by the intense heat generated during the explosion and subsequent fires, which created an environment where ignition was nearly inevitable. Once ignited, the burning graphite could have released significant amounts of radioactive isotopes such as cesium-137 and strontium-90, further contaminating the surrounding regions and posing severe long-term health and environmental hazards. Fortunately, the gallons...
Okay, cesium-137, 30-year half-life. Sure, that's just what actually happened.
The first responders prevented that situation from occurring, but had they been a bit later in their arrival, or a bit more, well, fuck this, we're getting out of here, when they started tasting metal in the air, this nightmare scenario could very well have played out.
No, not even a little bit of it.
In the aftermath of the Chernobyl disaster, sweeping changes were implemented to address the RBMK reactor's critical design flaws. The most significant modification was the redesign of the control rods to eliminate the graphite tips, ensuring that their insertion would no longer cause a temporary spike in reactivity.
Okay, finally he said something correct. I thought he just descended completely into madness for the past few minutes.
Additionally, automatic shutdown mechanisms were improved, and the emergency core cooling systems were upgraded to enhance reactor.
One other weakness they had for the RBMK was the control rods inserted pretty slow. It could take several seconds. A pressurized water reactor or a different type or a regular type of boiling water reactor could do it in less than 3.
During low power operations. Operational protocols also underwent significant revision. A stricter regulatory framework was established with enhanced oversight to ensure compliance with safety procedures. Training programs for operators were intensified, focusing on the importance of adhering to safety measures and understanding the unique dynamics of RBMK reactors. To date, 7...
they actually released technology on how this RBMK reactor should be operated.
RBMK reactors made are still in operation, but the extensive improvements have mitigated the risks that once made them so dangerous, and so these reactors are now considered safe, with international nuclear safety bodies acknowledging the effect.
They're safe, they're just old and still not the best type of reactor. The pressurized water reactors and boiling water reactors are better, and even those are old too, but...
The modifications, so no need to worry?
No need to worry, you need to quit spreading this information, man. This might have been one of the worst Chernobyl videos I've seen in a while. Thanks so much for the recommendation, and thanks so much for watching. I'll see you next time.